Yes, we can see your presentation.
Okay, so we discussed this one, of course, the bearing one. Now, I'm just trying to show a few structural efficiency charts, which are taken from John Hartsmith's work. The efficiency of a joint is defined by the eta joint is P maximum, that is the load P for the failure, that is the maximum load, divided by FTU WT, where T is the thickness of the plate and W is the width. FTU is the unknown strength of the laminate, or suppose it's a metal, so unknown strength of the metal or laminate in the load direction. This is just a crude definition. So the purpose of this is just to give you some feel that bolted joints, the structural efficiency, which I said yesterday, is low compared to the metallic materials. Because it's a brittle material. So this is totally brittle material, where you find the plot is joint structural efficiency, I defined on the previous slide, versus D by W. D is the diameter of the fastener and W is the plate width. So based on this, John Hartsmith has plotted based on the analysis of the joint failures. And what is said here, if it's a brittle material, then you find the structural efficiency maximum is around 30%. Now here in this region, there's a bearing failure initially, but as W reduces, diameter increases in comparison to the W, then we will have a net tension failure. So what you see here, there's a transition with the width of the specimen compared to the fastener. As yesterday I showed the chart, as you increase the W by D, the net tension failure changes to the bearing failure. So, or reverse, D by W, when you increase, is the tension failure, and at lower value is a bearing failure. So that's what you see on here. There would be transition somewhere. And you do not want, as I said, this mode of failure, tension failure mode you don't want. You want the joints to fail only by bearing. And I discussed that issue yesterday. For fibrous composite, even though they are treated as brittle materials, but what happens when you are loading the joint structure? Now here at the hole, because of stress concentrations over here, it creates some damage, like applied delamination, disbond, fiber failures, and that damage acts like a plasticity, a small amount of plasticity. And that is why, because that provides some relief to the stress constant factor, which I would be discussing when I'm discussing about notch analysis next week during damage tolerance. So that is why for fibrous composite, so this is lying somewhere in between the ductile material and the brittle material. On the other hand, like aluminum or some ductile other materials, then you can extract the efficiency to be much higher. So suppose it's an aluminum plate, aluminum to aluminum joint, you can get almost 70% efficiency of bolted joints. Composites, around 40% is the maximum. It's very difficult to achieve a joint efficiency beyond 40% for fibrous composites. So that means the structural efficiency is pretty low for bolted joint. If a structural efficiency low, that means what happens in order to improve the efficiency, you have to increase the fastener diameter, and then you have to increase the thickness, you have to increase the width. All this adds to the weight. So that way, compared to the metallic joints, composite joints would demand larger thickness, larger weight in order to achieve similar efficiency, and that will add to the weight. However, because the density is lower, you may have a compromise solution that it may not be significantly increasing the weight, but beyond the joints, you have significant reduction of the weight of the structure, and that is why overall the composites still provide you efficient structures compared to the metal, aluminum. And I had told many of the advantages during my certification course about the composites. Okay. So here I just provide the notes, what I discussed. I won't read them. Some design parameters summary. Clamp torque. That is, yesterday I discussed the joint has to be clamped up to 100% rating of the bolt in order to achieve high bearing strength, static, and also the fatigue strength. And if fatigue is affected significantly if you have the lower torque. Width to diameter ratio, in order to have the bearing failure and avoiding the net tension failure, you normally should have W/D greater than 5. End to diameter ratio, that is E/D, joint bearing strength, static and fatigue improves with increased E/D, so E/D should be greater than 2.5 usually. Countersink to thickness ratio, which I said should be less than 70%, usually is thickness is about 1.5 times the countersink depth. Fastener diameter to thickness ratio, T/D, for a single strap should be less than 0.8. And laminate thickness, bearing strength degrades with increased laminate thickness compared to bolt diameter, so T/D again should be lower. Layups. Yesterday I showed a chart that percentage 0 degree, and now somebody asked a question. Just I put a slide here. Let me explain you percentages just to highlight. Let me see, where is it? Okay, I put the slide today. Yeah. So layup designations. This is what I was trying to tell yesterday. I said, normally for a conventional layup, our design practice is to use 0, 45, 90, and minus 45, rather than using some odd layups like 10 degree, 20 degree, 30 degree, or 40 degree. We don't use that. Although there are some structures which are trying to use some non-conventional layups, but they are not very popular. They have some difficulties in design. So this is the most convenient currently, which is used by the industry, these 4. So normally what happened, designation when I was telling 40, 40, 20 or 10, 20, that means suppose this is a layup, 45 minus 45, 0, 0, 90. There are 10 layers. This S represents symbols, symmetry. So that means 10 layers. Out of 10, you can see 45 minus 45, 2 into 2, 4. These will be 4, and these will be 2. So that means in terms of percentage when we write, so this is the usual designation when we are expressing this 40, 40, 20 say. That means 40% 0. That's what I have written here. Percentage 0 degree plies first, then percentage 45 plies, and percentage 90 degree plies. So that means 40% 0 degree, 40% 45, and 20% 90. And this is usual convention, which you would encounter quite often in my presentations. Also, now somebody had asked about fasteners, and I was telling Professor Dinesh about design guide I have sent today, which is a file from NASA, which is about 20 meg, and it is in the directory. He has uploaded it, and that's a beautiful document about fasteners guide, design guide. It talks about various types of fasteners for aerospace, their material, thread requirements, thread sizes, collars, nuts, washer, everything which you require any guidance for the fastener design is given in that. So I would appreciate that those who are interested in fasteners, that document is very useful to provide you all information about the materials of the fastener, types of fasteners available for aerospace, and the nuts and collars and washers. That's a very good guide. Okay, now joint analysis and design. So let's discuss some of the parameters just to clarify what it is. If you have normally you'll have multi-row stacks of the fasteners pattern, and the way normally is designated, suppose the load is applied in this direction, the fastener pitch is considered in the load direction, the distance from center to center, and fastener spacing is 90° to the load direction. That is the usual convention. Fastener spacing, fastener pitch. Sometimes it's very confusing, sometimes confusing, somebody may talk about, okay, this may be pitch and this may be spacing, but no, this is usual designation, which is correct. Edge distance and distance, this is E2 is edge distance, and this is end distance. That's how we use the designation for these fasteners, spacing and edge distances and distances. Similarly, when you have a staggered row pitch, then we define some spacing like this one, and usually this. So our objective when we are trying to meet the requirement of WYD, say, we will consider, okay, normal to this, the distance from this fastener to any other fastener should be 5D or 4D, whatever the requirement is for the definition. Okay. Now, general design problem, general joint problem. What happens in a joint? The loadings are not always in one direction. Joint will be loaded in various directions. So you have 3 loads directions, NX, NY, and XY, that is shear and the axial loads. Plus there would be moments, which we are not showing here. Now, what happens when you're trying to analyze, this becomes a very complicated problem. When you have multiple fasteners and multiple loading situation. Okay, in order to analyze this, say, what we do, suppose we pick up this fastener. Then we will divide the loads. We define the loads. There are 2 types of loads now we are defining. One is the bearing load. Another is the bypass load. Now the bearing load we define, because what happens here, if you imagine a situation when you are applying a multi-axial loading over here, the load is being reacted by the fasteners. Now each fastener is reacting some load. Not equally, there will be unequal loads. So that means when they are reacting the load, there will be some bypass and some fastener reactions. So the fasteners, the load going through the fastener is the bearing load essentially. The load reacted by the fastener. But load which is not reacted by the fastener is just bypassing the hole or bypassing the fastener. And this is what it is. So this is bypass load and this is bearing load. Now, important thing is over here in composites that we need a separation of the bypass load and bearing load in order to analyze the joint. And in metallic structures, for static, usually we do not consider the interaction. But for fatigue, of course, in metals also interaction of the bearing and bypass is considered in order to determine the fatigue life. Because as I showed yesterday, that at the smaller loads, the load distribution are unequal between one fastener to another fastener because of the material does not yield at that load. And that is why at the fatigue loads, you don't consider any yielding of either fastener or the aluminum. And that is why the bearing and bypass interaction for the metals is also considered for fatigue. But for composites, even for the static, we do consider bearing and bypass, and becomes a big issue. There are a lot of methods, a lot of theories developed, computer softwares available in order to analyze the bearing and bypass interaction. It's not a simple problem, in fact, for multi-axial loading to analyze those bearing and bypass interaction. And I will be talking in this lecture about such an interaction phenomena. Okay, here I'm just showing you the picture of bearing bypass just to make it clear what do we mean. So suppose you have a joint where the load is a P and it being shared by two fasteners, so P1 and P2. Now, generally in this case, we will assume P1 and P2 are equal. They are two fasteners only. If there are three fasteners, of course, they become unequal until they start yielding. So that means I can split this part and this part. If I'm taking the free body diagram of this, you can see this is the free body diagram of this one. That means I have the load P applied here, and only P1 is being reacted over here at the fastener. That means the remaining load has to be P minus P1 over here. Okay. And then plus, that means if I'm cutting the section here, so that means this fastener P minus P1 and P2 is here. Now P1 and P2, they're equal, which is P by 2. So this is the bypass load, P minus P1. You see, this is getting bypassed. It's not being reacted by the fastener. If it's not being reacted by the fastener, the remaining load, which is bypassing the fastener, that is what is bypass load. Any questions about this? Is by bearing bypass clear? Okay. When you have a compression, similar story, I won't explain that, it's self-evident. When you have a shear, in shear case, it's a bit tricky. I've tried to draw a free body diagram. So this is single fasteners, and you have some loads applied, NX, Y2, and from this, what happens then? Part of the load will be directed to fastener. So here I've shown some NX, Y1 as a bypass, and this is equivalent to this free body diagram. So I'll just say first this one, NX, Y1. I'm saying this load is just a passing through the fastener. It's not being reacted by the fastener. So this is bypass, and the remaining loads, you can draw the free body diagram like this one and calculate these loads I've just shown here. Say PBX, this load is 0, and PBY would be reacted as A. A is this dimension multiplied by NXY2 minus NXY1. Okay. So this is the story about the bearing and bypass. However, what happens is very simply said than done. When you have this complex structure like this one, it is extremely difficult to decide bearing and bypass segregation. And especially when you have the finite element methods being used here. So finite element method, what will happen is, depending upon the element sizes, each element loads will be different. And now from that element loads, you have to extract and decide how much is the bearing and bypass. And I can tell you, surely, it becomes extremely difficult problem to pick up the loads from the FEM output for the elements and then trying to decide, because what happens when you are modeling, you will be modeling fasteners as the locations, so they will be reacting some loads. And so, of course, that is easy. Now, bypass becomes difficult. So in Boeing, of course, Boeing had developed some methods how you predict the bypass loads from the FEM output, and they had just derived a method, and that simplified determination of bypass loads from FEM output. Now, I can't go into the details of that. It's a bit involved. And of course, I can't give what is the method of the Boeing here. But anyway, that's not needed. The important thing is just to understand the bearing and bypass definitions. Okay, now metal and composite joints, fastener load distribution. I think I showed this graph. I won't repeat this. And I've already said, but I just said the difference between the metallic and composites. So analysis joint is strap metal, static ultimate, bearing bypass interaction, no. And as I said, in static, you don't consider for the metal joints. Or fatigue, yes. Composite, yes, yes. I already discussed that, honey. Now, joint analysis. Determination joint load, bearing and bypass loads and tension loads. Analysis of joint for bearing and bypass bearing, bearing bypass interaction, margin calculation, other modes of failure such as shear out, net tension and cleavage failures. They have to be also analyzed in addition to bearing bypass interactions. Bolt analysis, bolt bending, shear, tension, which I'll be showing in this presentation, each modes of failure calculation. Bolt pull-through, shear interaction. Now, joint load determination. So, it's a complex analysis when you are trying to determine the load share, because each fastener will be different loading. And in order to determine that, if it's a simple unidirection and you have only two fasteners, it's easy to analyze, consider, okay, how much is each fastener is taking the load. But the moment it becomes even three fasteners in a row, it's difficult because the loads are not equally distributed on each fastener. So we use the load share analysis, and the load share analysis has been developed. The software is available at Boeing, of course, and they use various methods, two-dimensional joints and single one-dimensional joints with thermal effect, strap thickness, diameter, fasteners, fastener type, stiffness, because what happens, they are based on the spring action. Fastener is considered to be in a spring for the analysis. And then you use some energy methods or force equilibrium method to determine the load shared by each of the fastener. Now, I won't go into the details of that. And if you want some idea, is one of the NASA reports, which I sent yesterday, which is by John Hart Smith. You can get some idea about the load share analysis. But I have not put up in this presentation. It's a bit involved. I could discuss later on sometimes, but not now. Okay, finite element method is applicable to complex structural details of multi-axial loading, which provides the load share analysis. The FEM method is capable of modeling the large portion of a structure, so only joint or multiple. So if there's a complex joint, normally you would be doing the finite element of large structures, and the joints positions will be modeled, which will provide the fastener loads, and also then pick up the element loads using those element loads calculate the bypass loads based on the procedure developed. Okay, now load share by observation. I was just trying to show, okay, suppose you have a case here, single fastener, this single row of fastener, multiple fastener, they are all. Okay, now suppose you have NX here, NX load coming, so NX, NX, NXY, NY normal to this one. I have not shown here like this one, NY, NY. So what we are saying, okay, from this fastener to this step to this step, the load has to be transferred. Equilibrium has to be satisfied, the same loads. Now, NY is considered just passing without changing or without being reacted by the fasteners, NY load. So I've shown here, NY is not being reacted by the fasteners, where NXY and NX is being reacted by fasteners. So I'm showing over here. So I pick up this fastener, say. So if you look into the free body diagram for this fastener, what will happen? From one step to another step when the load transfers. Okay, so I take this is a free edge. You can see this is a free edge. Okay, so there's no load over here at the free edge. This load NY, I said it doesn't get reacted by the fastener. We are just bypassing this load NY for simplicity. Okay, so that means there's a shear NXY because that shear is here. So that shear has to be there, this one, and this NX load. And from where the NX comes then, NX has to be reacted by the fastener to satisfy the equilibrium. Okay, same thing, NXY, because this is NXY here, and this will be not in equilibrium if fastener does not react this load. And this is what I've shown here. Suppose splitting this one, so NX this plus NXY, this will provide this bearing load, and NY just gets bypassed. This is two holes. I won't go into the details of that. You can just, those who are interested can go through this free body diagram and try to understand this one. So I've just shown over here the values calculated for these fasteners, which should be easy to understand. So I won't spend time in discussing this. The simple free body diagram and the equilibrium conditions will be satisfied. Okay, now one-dimensional analysis, one-dimensional joints, if we are considering, say, there are multiple fasteners, like 4 fasteners, and in order to do the load share analysis, of course, as one can consider the fasteners at the springs and stiffness characteristics of each one and write the equilibrium equations to determine the fastener loads on each one. They will be unequal. Now, I've taken this example from the joint load distribution done by John Hartsmith, just to illustrate the point of unequal load distribution. So you can see here, this is half-inch thick strap. 1, 2, 3, there are 4 fasteners. All fasteners of the same diameter. And you can see the result. The middle fasteners, they pick up lower load, and external fasteners pick up higher load. So you can see here, if I consider this to be around, say, 11,000 pounds, and this is about 8,000 pounds. So the ratio would be almost 30% higher, these loads compared to this one. And that is why one has to be careful when designing the composite joints that you cannot assume that each fastener is sharing the same load. It is very risky because you may feel the joint. You would have calculated the margin to be positive, whereas in real sense, the margin will be negative and the failure might occur. So one has to be very cautious. And this is why in composites, this phenomena is very important to be considered. So just those of you who are going to join the industry and they have to deal with the joint, just remember one thing: fastener loads are not distributed equally in composites. Now here, if you have a tapered structure, this inner step is tapered. Normally we don't use this. This is just a case we are trying to show the load distribution, what happens. In this case, the load distribution is more of uniform. Again, I won't go into the depth of this one. Generally, we don't use this structure. We can consider that to be hyper. Another case here, now configuration B. This A. Oh, this is duplicate. Don't worry, this is configuration C now. So board C here, now we are tapering the external members. And as you can see, this picks up the highest load and then other fasteners pick up almost similar load. Joint C is the second weakest joint. This is a very weak joint, not preferred due to interlaminar weakness associated with tapered members. So this is also not preferred. Another one, configuration D, where what is happening here, you are tapering, but the fastener diameters are different here. In this case, fastener diameters are same. In this case, fasteners diameters are different. So what happens here, the large fastener diameter, it will pick up more load. Anyway, this was picking up higher load in the previous slide, but now since you have larger diameter, it will pick up even higher load. So this is optimum design. Design maximum the bypass and minimum bearing stress to the first row built and highest bearing on the last board, where bypass is 0 on that. However, again, this is again impractical to design the joints. So always you will find, rather than tweaking the tapering, we don't use that. There are hypothetical situations which have been put over here just to illustrate the effect, but in practice, this type of joint only will be used generally. Sometimes what happens, in this I'm showing the constant fastener diameter, but sometimes we'll have, if the load is very high on the first fastener picks up and it can't take the load, that means we'll increase the diameter of this fastener. But the danger to that is, the moment you increase the diameter, it will pick up even higher load. But there's a compromise solution then to be obtained when you are tweaking the diameters of the fasteners. Okay, joint load distribution parameter dependence. What are the parameters which affect this joint load distribution? Strap material and thicknesses, hole size, fastener type and material, hole clearance, fastener pitch and spacing, edge distance, strap width, temperature and moisture, strap tapers, joint tape types, single or double shear, shims types, and materials. Joint failure analysis now. Some of the modes of failure I'm trying to put over here, simple analysis. Causes of tension failure. We are considering tension failure over here, that net tension failure, where one of the effect is width of the coupon or member is smaller or W by D less than 3, it will encourage the net tension failure. Layups, material and layup. You have a 90-degree dominated layup and low 45 plies, then it will encourage again net tension failure. So net tension failure load simply can be written as PT into KT. KT is a net tension stress constant factor, or else you can write in terms of a gross stress constant factor, but this is derived on a net tension stress constant factor W by D minus 1 into dt and Ft. Ft is allowable tension stress for laminator load direction. So this is simple tension relation. I won't go into the details. Then shear out failure. So shear out is a load applied over here. If you have too many zeros, less number of 45s and 90s, then this will just pull out like a plug. Shear out failure. So now it depends. And the E by D is small. So short edge distance, poor layup, that is very high 0 and low 90 and 45. Shear out failure load can be written as simply, this is average, basically. But someday, no. Could be there's some stress constant factor applied, but we have not considered that. So this is in general used like that. Similarly, bearing is very easy. Bearing failure, stress is D, T, FBR, bearing stress allowable. Okay. Cleavage tension failure, there's no simple equation. I have not written simple equation available for this one and wouldn't worry about. Cleavage, again, this is again a very approximate relation. If this is a fracture plane, so average stress to failure is applied over here, FTU into T, E minus D by 2. But I question this equation because it's not that simple the way the average stress will be behaving here. The fracture will start by some stress concentration, so it's that factor. So again, this is a simplistic equation. Fastener joints, bolt bending failure. Now, bolt bending failure, I have not provided any method over here in this slide, but if you wait, I've tried to discuss the bolt bending calculation because that's very important. Here in this slide, I just tried to show the restrictions. We must design the joint to avoid this failure like this one with a T1 by D less than 0.8, T2 by D 0.8, and TS, that is total stack thickness, to be less than 1.6. It's important because we have seen lots of failures during testing when we had thick straps compared to the fasteners. And I'm very particular about it, that guidance. What happens here? There would be always attraction. Okay, when you have some bearing allowable data, suppose we are dealing with about 600 megapascals of bearing stress allowable joint, and you choose a fastener like a 6.4 millimeter or quarter-inch diameter fastener. And okay, your load is particular some amount of load, and then there's attraction to use. Okay, I'm trying to design the joints, and doesn't matter if I've chosen a quarter-inch fastener, 6.4 millimeter fastener, and this is my allowable, so I can keep on increasing thickness until I achieve my margin to be positive. Well, there's a danger in doing that. You have to carefully watch that you do not keep on increasing the thickness and violate this condition. You will fail the bolt rather than the bearing. So it's an important recommendation. Just to remember this criteria. I mean, it looks simple, but I tell you, joints failures occur due to this phenomenon. When designers don't follow certain guidelines. Fasten joint bolt pulling through the laminate. Say this pulls through. Possible causes usually associated with countersink fasteners and thick laminates. Once again, the bolt bending is related to the thick laminates, then pull through. What happens if bolt bending occurs? Then it tries to pull the fastener, and it causes pulling through mode also. So bolt pull through, and bolt bending, they are related basically. Bearing and bypass stresses. Just trying to show some analysis, simplified analysis method. Okay, now the bearing distribution, bearing stress distribution and bypass stress distribution here. Suppose you are applying the load over here and this is P, and so due to this one, the load has to go through this corner. So that means here what is happening, the stress distribution, tangential hoop stress distribution. The maximum stress will occur at this, and then it will decrease. The distribution, what has been found by the analysis, the analysis done by Bickley, almost, you can say almost 100 years back, published. And he provided the guidance that the maximum hoop stress in this case is about P by dt. Now you will remember the situation. P by dt is equal to the bearing, average bearing stress. Also we write bearing stress is equal to P by dt. So this is equal to P by dt, bearing stress equal. This stress, the maximum bearing stress over here, although we consider P by dt as an average bearing stress, you don't want to consider the maximum bearing stress, which is 4P by pi dt. Now, in the next slide, I've derived this expression. How do you get this maximum? So this is equivalent to this sigma max stress, maximum tangential stress at a point due to bearing load. Okay, I won't go into the derivation. This is a simple derivation, and from geometry and the pressure distribution, one can derive, okay, assuming this pressure and cosine distribution for the pressure, that's what you usually assume. This pressure distribution is cosine distribution. So based on this one, this is nothing but integral of this force pressure, and one can calculate, and I've shown over here the P max. You can see this P max, which I was writing, this one, 4P by pi dt, and this is 4P by pi dt. So this is a derivation, which is simple to understand. I want to spend much time in going through this one. And average bearing stress, FB average, is P by dt. Okay, now, after this one, so PB, if we are trying to analyze this single hole stressing bearing, so PB is being reacted, going through the here, reacted by this one, so that means PBA at B and A. What are the maximum stresses? Sigma max A, we consider KB into sigma bearing. So some stress constant factor for the bearing, and sigma bearing is PB by dt, bearing stress, which we showed in the previous slide. However, if you remember from the previous slide, I showed that maximum stress at this point is about P by dt, which is equal to FB. And that is why I have said here KB equal to 1, even though I'm writing here KB, but KB is 1 for elastic analysis. So maximum bearing stress at point B is given by this one, which is of course 2. That means maximum bearing stress is, if I consider this as FB, average stress, FB 4 divided by P. Okay, pi. Single hole stress again, so maximum tangential stress at point A due to bypass are given, and this we are considering by bypass. In the previous slide, it was bearing. Now we consider at this point the stress due to bypass, sigma max 2. So sigma max 2 is KT into sigma bypass, and sigma bypass is P bypass, that is load, divided by WT. A stress constant factor, KT, is expressed as for a large W by D as this one. And if there's a whole correction factor to be applied, because W by D effect will be there, which I didn't write it over here, but that's given any book. Even Rourke gives it. I could write it next time, but I read that. I forgot to write. Anyway, this is for infinity. So total stress at point A, we consider, okay, bypass the bearing. So at this point, and what I'm trying to explain, the importance of bearing bypass interaction, why it is important to understand. So you see here, this one, we are applying a bearing bypass, here the bearing. So for a joint bearing, the total stress sigma max at this point, because a failure may initiate from here, equal to sigma kb into sigma bearing plus kt into sigma bypass, and sigma max equal to then kb into sigma equal. So for failure, at this point, that means the failure would occur when the total stress, sigma max A1, sigma max at A, and this A due to bearing, they together approach FTU, which is allowable strength. So FTU being a notch laminate strength, then the failure would occur. So this is our equilibrium equation for the failure. So single stress continue, okay. Now, what we wrote here, KT and KB, they're the elastic stress constant factors. But what happens when you are applying the load, and due to load, the laminate near the hull gets damaged. Damage in the sense there would be some small amount of damage developed, like a fiber cracking, fiber to matrix crack, delamination locally, and some fiber failure if they are very high stress. So like this damage. So the effect of this damage is, say I've shown here, if there's a stress plot, sigma mass elastic, so it will be reduced. Now, actual what happens because of this damage, the maximum stress will come down. This will relieve the stress constant factor, so your reliable goes up. So what happens is KB and K, instead of using elastic stress constant factor, that will be conservative. Well, if one could reduce based on some test data, that will remove the conservatives and get a better allowable. Multi-row fastener joint. Similar analysis, again, I may not go into the details of this. When you have two fasteners, again, bearing and bypass, they are being added here, say, and total stress sigma max 1 and 2 will be added for the bearing bypass interactions. And similarly, I have just derived some expressions here. So sigma max, that was due to bearing and bypass on those fasteners which I showed previously. So you have sigma max 1, sigma max 2, KB, sigma B, and KT, sigma T. This is similar expression what I discussed for single fastener. Okay, again, this is very obvious to read here. So you calculate from here, sigma B is this one. And for failure, that means if we are writing sigma B, it must be equal to FBR. The bearing failure would occur when the bearing stress reaches the allowable. So this is the equilibrium equation for failure, and that will represent the optimum joint design. Okay, now bearing and bypass analysis, when we are doing, there are two methods available for bearing bypass analysis. One is using the interaction charts, and I'll explain in the next slide what does the interaction chart mean. And another is the point stress criteria. Now, point stress criteria has come from a open hole and cracks that was proposed by Whitney and Newsmer in 1973, which is very well being used in order to analyze the notches and holes in the laminates. And this is what I will cover, the point stress criteria, next week when I'm talking about the damage tolerance analysis. It's an important method, very simple, it's very useful method to predict the notch strength for the laminates. There are many methods which we'll be talking, but this is the most popular method which I like, point stress method. So for that notches and holes, the same philosophy has been used here. The point stress method is being used for the loaded hole also. In order to analyze the holes with the fasteners and consider the bearing and bypass interaction. The point stress criteria just tells us that you have some applied load, say, and then this is a stress variation, as you can see. So here, suppose it's isotropic material, this will be 3 sigma maximum stress. In composite, it could be 2.5 sigma, it could be 6 sigma depending upon the layer. So assuming this is a variation, what the point stress criteria tells us. The criteria is that at some distance from the edge of the hole, suppose this distance d naught t, this stress which is dropping at this point, the failure would occur when the stress at this distance reaches the ultimate unnotched strength allowable. Now, normally you would consider, oh, why don't we consider the maximum stress at this point and then compare with the unnotched allowable? What happens? That will be conservative. This phenomena is coming up, and I'll explain this more in detail when I'm talking about the notch analysis. It's due to some damage development around the hole edge. So the damage, when it develops a small damage, which is like a plasticity in metals yield, and that means the stress constant factor for the metal never remains as 3 sigma, it comes down. It may be 2 sigma, it could be even less, depending upon the yielding. Same phenomena is occurring over here in the composites. A small amount of damage relieves the stress concentration, and that is why we are trying to take advantage of the reduction in the stress concentration to determine the allowable or the capability of the hole, which improves rather than using simply stress constant factor. But I'll discuss this in detail later on. Okay, now bearing bypass analysis when we are doing, I showed in the previous one, bearing bypass interaction charts, which require interaction charts for various loading situations using test data. It requires lots of test data, and I will explain that. It requires large test matrix, limited applicability in multi-axial loading. However, this method is very powerful. Fewer tests required, no limitation of applicability of multi-axial loading, and this is valid for any type of loading, whereas this is very limited in application. So this is more versatile. Method 1, which is based on the single fastener data, I'm trying to discuss over here now. Method 2, based on the 2 or 3 fasteners test data, and I'll discuss that the method 1 said. So I provide some references. Okay, this one bearing bypass I already showed. In order to generate the bearing bypass interaction, we require some test data. Test data is needed for unnotched laminate tension strength, unnotched laminate stiffness, unnotched laminate compression strength, open hole tension, filled hole tension, open hole compression, filled hole compression, and single fastener bearing test. So these are minimum tests required in order to generate the test data based on single fastener. But I'll discuss that this is not very useful. We need to use 2 fasteners test data. Again, this is similar diagram which I showed previously, and now here I showed earlier, so I won't go into the details. Repeat it. So based on that equation, which is this one, I converted to the strain here and written down E bypass divided equal to sigma bypass upon E, and this is what the equilibrium is. E is the elastic modulus in the direction of the loading. We define the failure strength for the coupon with the whole of diameter D as En allowable, which is a allowable notched strain for the either it could be for a filled hole or for open hole. It should be, I've said here, En allowable, notched strain allowable, lower of filled and open hole, because sometimes the filled hole with the fastener gives a lower value. Now that will explain next week how the filled hole, open hole tension values vary based on the layup. So, and this is unnotched allowable FTU by E. Just written down the equation. I won't go into the details of that. They're self-explanatory. So based on this one, we write an equation, E bypass equal to En allowable 1 minus sigma BRG. And all these terms are explained here. So I won't go into the details. It's just a simple equation derivation. So what we have done here by this equation, we have tried to relate the bypass strain to the allowable, that is notched allowable, and this is bearing stress and E naught, which is unnotched strain allowable. And so based on that, we plot that equation, En allowable versus, E bypass versus the sigma bearing. So this provides us some kind of an interaction chart. But really, we are not using this one. I'll use two fasteners interaction chart. Failure equation, E bypass equal to En allowable. So this is the failure equation in order to determine. So what happens here using this chart, suppose I have the bypass strain. Suppose this is my applied bypass strain, and this is my bearing. So that means the failure would occur at this point. And that's what the utility of this chart is in order to define the interaction between bearing and bypass. That's what it's doing. So you're plotting the bypass and bearing stress and determining margin based on this chart. And let me just tell you, because what happens, this I have shown simplistically for one. However, this is a function of various parameters, which are joint type, geometry, hole size, laminate material, fastener type. So each of these charts will differ based on the joint type, materials, environment, hot or cold. Now, instead of the single fastener, so I've just put some comments here. Tension bearing bypass interaction based on the assumption that KB equal to 1. However, KB is not equal to 1 depends on the layup. Usually is less than 1. To resolve such an issue, better to test multi-fastener, two fasteners, and shear to obtain a data point on the bearing bypass interaction to validate the bearing bypass interaction. So I've shown here the two fasteners interaction. Yeah, I think I might invite the questions because I've been talking, and then I would like you to discuss rather than just continuing the discussion, my lecturing. So let's see the questions, please. Any question? From anyone? Nobody? No question? Was it too much? Couldn't make you understand? Hello? Anybody? Any question? Or I'll continue then.
Looks like nobody else has questions, Dr. Kar. Maybe you can continue.
It seems maybe it's a bit difficult concept really, bearing and bypass interaction, it seems to me. And that is why I just want to know if it's just difficult to understand because there's a lot of these. I might simplify the discussion. I don't expect them to understand everything, of course. I just want to provide them that there's something like these analysis techniques.
Right.
Yeah, I understand it's not easy to just.
I think it's more of
within a few minutes to grab all the concept.
Hardly anybody I see here in the group is working on bolted joints as such. So it's kind of an exposure to a new topic for them. So they might have gone through some basics of bolted joints, but not in the way it is practically required in the industry. So I think it's a useful addition to their knowledge.
Yeah, that's what I think is a good idea, because I don't expect them to digest everything here. Just the idea is to give them or make them familiar about what is to be done if they have to analyze the joints sometimes, right? And then they can refer to the literature.
True.
Okay, now I think then what I'll do then, I'll discuss two fasteners and then other things next week then.
Sure.
Rather than rushing, I give the students time to digest this material. In fact, it's going very slow then again.
Right.
Shall I cut down some material out of it and skip? Do you think, Professor Dinesh?
It's fine. If you want, you could extend 1 or 2 classes a little more than 1.5 hours if it's not too tiring for you.
No, it's not tiring. Unfortunately, what I told you what happens after this next week, I have to deliver 14 lectures, and that's very tight schedule with IIT Dharwad, 3 lectures a week.
Sure.
Now, I could take up after I finish with them, sometimes after middle November. I don't mind going into the December.
Sure. December would be a little tough for the students because they would have their final exams.
Yeah, I appreciate that. It may be difficult then.
Right. So it would be good if we can finish it. When would you be done with the IIT Dharwad lectures?
I think they wanted to finish by 10th of November.
Okay, so I think the second half of November should be okay. As long as we don't stretch into December, I think that's fine.
Yeah, that's fine with me. Let's see how we go. Because I was thinking about damage tolerance analysis, that notch analysis and all that. I don't think the way I'm going, that it may take about another 2 lectures to finish up the bolt.
Okay. Yeah, I think there are some students who are working in the area of damage tolerance, so that might be something that they would be far more interactive about than the bolted joints, which is of course equally important. So I'm not surprised that there are not too many questions.
Okay, so that means I can drop this and then take up the notch analysis if that is more interesting.
No, I would rather have whatever you have planned for us, but we could probably spread it out to the second half of November after you're done with the IIT Dharwad lecture series.
Okay, that's fine with me. Let's see how we go.
Sure, sure. Yeah, because what you're sharing with us is not readily available elsewhere, either in textbooks or in other forms of lectures.
Yeah,
So
textbooks.
we really would like to utilize your expertise and humongous experience in this. So we'd not like anything that you've already prepared for us to be shelved.
Yeah, that's right. You won't find in any of the books this material here, the like voltage, the bolt bending calculations, this material.
Yeah, once in a while, because of clashes with other classes, maybe the attendance is a little thinner, but a lot of them are watching it after the recording is done. So whenever it's convenient for them. So it's something that will stay with us for a while.
Okay, that's good. So, in fact, these notes have taken a lot of time. It's not simply, in fact,
Yeah,
I built up over
effort.
several years because I was delivering lectures at Boeing also.
I see. Okay.
Every batch I've delivered almost, I used to deliver to local, the new hire engineers they were hiring.
I see.
And then I would deliver the lectures to them. Of course, I have
This is part of
updated
their
now.
regular orientation program, is it?
Yes, so I delivered lectures almost like 20, 25 hours of lectures every year almost. Various aspects of the composite structure design, analysis, and a lot of material then I will draw from Boeing literature, which I can't show here. I don't have now here. So, and of course, these notes, what happened now, I've updated everything. Each slide is updated after my retirement. So, okay.
That sounds good. Yeah. So we'll catch up on Monday at 2 p.m. IST.
Yeah, okay. Now, 2 p.m., is it convenient because many of the students
Yeah,
have a
there is a
clash?
clash. So, but I don't know. It's kind of a compromise between having you stay awake for so late in the night and having more students.
I think it's okay. I can just, because I would like the students, if I'm working, let the students gain. So maybe 3 o'clock. If 3 o'clock is convenient, just shift it to 3 o'clock then.
Right. Yeah. Because Mondays, Wednesdays, and Fridays, many students are having this 2 to 3 class. So
I think
that might be one
because
of the main reasons why we have less attendance today.
I think it's a good idea then to shift and make it convenient. Let others benefit otherwise.
So next week, all 3 days, Monday, Thursday, and Friday.
Yeah, make it like 3 o'clock. I would just.
There's no confusion. If it's one day 2 and another day 3,
No,
then
make all that 3 o'clock. It doesn't matter actually. It
Sure.
doesn't matter. 1 hour late.
All right. Yeah.
You
really appreciate that. That's kind of you.
Because my objective is to provide information to the students. If I'm working, let them get the benefit. And that's what my objective is. I decided that after retirement, I would give everything voluntary to everybody. Consultancy or anything, if somebody wants, I'm not charging anything. And that was the motive I had after retirement, and I'll be following that.
Amazing. Really nice. So thank you, Dr. Garg.
Okay, thanks.
We'll meet at 3 p.m. IST on Monday.
Sure. Thanks. Bye.
Bye-bye.
Thank you, sir.